Hello everyone, and thank you for watching our final design presentation for our senior project, SignFlex. Our team consists of 4 members, myself, Antonius Reyes, and Ryan Rahru, both studying computer engineering, Madison Vassar and Esteban Reyes, both studying electrical engineering. So what is SignFlex? SignFlex is a wearable smart glove that translates the American Sign Language alphabet into text and speech in real time. The main purpose of this glove is to bridge communication gaps between individuals who rely on ASL and those who don't understand it. Our motivation for this project came from a real-world communication barrier faced by the deaf and hard of hearing community. While many individuals rely on ASL to communicate, not everyone around them can understand it, which can create significant social and professional limitations. We saw an opportunity to use wearable technology to improve real-time gesture recognition and make ASL more accessible. Our goal wasn't just to build a translator, but to inspire more people to learn ASL by offering an interactive, efficient, and educational tool. It's also important to note that ASL is the third most used language in the United States, with over 6.4 million adults relying on it, so the impact potential here is very significant.
This slide outlines the key goals and objectives for our project SignFlex. Our basic goals focus on the core functionality of the system. First, we aim to develop a smart glove that detects American Sign Language gestures in real time. These recognized gestures will then be displayed on an Android mobile application. We're integrating computer vision using a smartphone camera to assist with gesture detection and boost overall accuracy. Our Bluetooth communication between the glove and app is critical, and we've made it a priority to ensure seamless data transmission. And finally, we're designing a user-friendly interface so that the app is accessible and easy to navigate. For our advanced goals, they are geared towards pushing the glove's potential further. We plan to implement machine learning to refine gesture classification over time. We're optimizing Bluetooth transmission to reduce latency and improve overall responsiveness. And we're working towards customizable gestures so users can personalize their glove's functionality to their unique communication style. Our objectives tie these goals together and keep the user experience at the forefront. We want to provide real-time feedback on gesture recognition. The app will be tightly integrated with the glove for seamless communication. Since this is a wearable device, comfort and flexibility are essential for long-term use. We're also ensuring that the glove can detect gestures involving both finger movement and hand orientation. And finally, we've included a battery monitoring system to alert the user when the battery is running low, helping ensure reliability during use. With these goals and objectives, SignFlex is designed to not just be functional, but intuitive, adaptable, and accessible.
On this slide, you can see our engineering specifications. For our specifications, we chose the following: size, weight, sensor sensitivity, temperature range, power consumption, memory usage, processing speed, cost, and accuracy. For our two chosen specifications, we chose the processing speed of both the flex sensors and computer vision, as well as the accuracy for the combined system, including the flex sensors and computer vision. For our processing speed, our specification is that it cannot be slower than 200 milliseconds, and for our accuracy, we're looking to achieve an accuracy of 85 to 95% with both the flex sensors and the computer vision.
This is our house of quality, which shows how we've connected customer needs to technical features. On the left, we've listed what users care about, things like affordability, battery life, and portability. Across the top are technical specs that we can control, such as size, power usage, and accuracy. The symbols in the middle show how strong the connection is between each need and feature. For example, portability strongly depends on size and weight. At the top, the triangle section shows how the technical features affect another, like how improving one might hurt another. At the bottom, we've added our target values, like keeping power usage low and accuracy in between 85 and 95%. This helps guide our design to focus on what really matters to users. Here you can see a visual representation of our product, the SignFlex Smart Glove. This slide will help break down on how the different subsystems are physically laid out onto the glove. Starting from the top right, you'll see the flex sensor connections running along each finger. These are responsible for detecting finger bending, which is essential for identifying the ASL gestures. To the center of the glove, this area is designed for the PCB storage. Our PCB houses the ESP32 microcontroller, the accelerometer, the battery monitoring system, and our voltage regulators. Keeping these components in the middle allows us to manage our power distribution and signal routing more efficiently. On the bottom right, you'll see the battery wires, which run to the opposite side of the glove. That's where the batteries are actually stored. We designed it this way to balance the weight and avoid bulkiness on one side of the glove. Overall, this layout helps ensure the glove remains wearable, flexible, and functional while maintaining accurate sensor readings and system performance. This is our hardware block diagram showing how all the components are connected. At the center is the ESP32 microcontroller, which handles inputs and communication. It takes data from the flex sensors and accelerometer and sends it to the camera app and external Bluetooth module. Our power comes from a lithium-ion battery, which goes through a buck converter and voltage regulator to provide stable power to all parts. We've also included a battery monitoring system to keep track of our power levels. Each wire type is color-coded, and the legend on the left shows who worked on which parts. And now we will take a look at our hardware comparison and selections. For our first choice, we'll compare two common processing units, the FPGA and the microcontroller. An FPGA, or Field Programmable Gate Array, is a reconfigurable hardware device. It's great for high-speed parallel tasks like AI, image processing, and encryption. But it does require HDL programming like Verilog or VHDL and tends to be more expensive and power-hungry. On the other hand, a microcontroller is a compact chip with a built-in CPU, memory, and input-output ports. It's ideal for low-power, real-time control in things like IoT devices and wearables. It's much easier to program, usually with C or C++. It's also cheaper and more energy efficient. So, while FPGAs offer more power and flexibility, microcontrollers are often the better choice for simple, cost-effective applications.
As you can see on this slide, we've compared the microcontroller versus the FPGA for our project. We've decided to go with using a microcontroller as they're more suitable for SignFlex than an FPGA. FPGAs would be overpowered for this application, and microcontrollers are more cost-effective and easy to program with C and C++. The integrated libraries also simplify the sensor and communication module handling, and they're designed to be low power, which is crucial in wearable technology. And we're able to integrate ADC conversions and analog data from the flex sensors.
A flex sensor is a bendable component that acts as a variable resistor. As the user bends their finger, the sensor's resistance is changed based on the degree of flexion. This data is sent to the microcontroller, which processes it and translates it into the gesture of an ASL letter or word. It's a simple but powerful way to detect finger movements in real time.
For the flex sensor selection, the team decided to go with the Spectra symbol flex sensors as they're best suited for our SignFlex project. We decided to opt for 3 4.5-inch sensors and 2 2.2-inch sensors to account for the index, middle, and ring finger, as well as the pinky and the thumb, which are shorter than our other fingers. These flex sensors have high durability and compatibility with wearable technology and make a great choice for our SignFlex project.
An accelerometer measures acceleration forces, both static like gravity and dynamic like movement or vibration. It tracks motion in three-dimensional space, helping us detect tilting, rotation, and directional movement. In our system, it works alongside the flex sensors to capture more complex hand gestures. This improves the accuracy of the ASL translation by recognizing movements that go beyond just finger bending. For our accelerometer selection, our team decided to go with the LSM6D-S3CR as it's the best choice for SignFlex. One of the key reasons is its low power consumption, as it uses only 0.9 milliamps in active mode, making it the most efficient choice for our battery-powered system. Additionally, it's a compact size, making it ideal for wearables and ensuring a comfortable design. It also provides a wide sensitivity range that allows us to track precise hand movements with high accuracy. The data rate gives us a good balance between performance and efficiency. With an operating voltage of 1.7 volts to 3.6 volts, it's fully compatible with our system, and its mid-range price makes it a cost-effective solution without compromising functionality. All of these factors make it the best choice for ensuring smooth, reliable, and energy-efficient motion tracking in SignFlex. A fuel gauge is a battery monitoring system that tracks the state of charge, voltage, current, and sometimes temperature in real time. It's crucial for preventing unexpected power loss, especially in wearable devices like our SignFlex glove. In our setup, it continuously monitors the lithium-ion battery and sends data to the ESP32. This not only helps maintain performance, but also adds an important layer of safety and reliability to the system. For our fuel gauge selection, the team decided to choose the BQ27441G1B because it's optimized for single-cell lithium-ion batteries like the one used for SignFlex. It uses I2C communication, making integration with the ESP32 simple and reliable. The chip also has low power consumption, which is key for preserving battery life in wearables. It's also a well-documented chip by Texas Instruments with strong support and proven use in embedded and consumer devices, making it a trusted, practical choice for our system.
And now we will talk about the power storage. Here is the power distribution table, which highlights each major component listed along with its input and output voltages, current draw, and total power consumption. As you can see, the ESP32 microcontroller and the AMS117 voltage regulator are among the top power consumers, drawing about 1.65 watts and 1.7 watts respectively. The buck converter is also critical in stepping down our 7.4 volt battery input to a stable 5 volt output. Lower power components like the accelerometer, fuel gauge, and CP2102 USB to UART bridge consume only a few milliwatts, while the flex sensors as a group draw around 5 watts, making them a significant contributor to total power usage. The power consumption of the overall system is about 9.26 watts. We chose lithium-ion batteries due to their high battery capacity for longer usage and are lightweight and comfortable, meant for a wearable device. They also provide a stable voltage output for the sensors and the microcontroller, and they generate less heat compared to the other options in this list. For our voltage regulators, we chose the buck converter and the linear regulator in order to distribute the power from the main power source. For the 5-volt line, we used a buck converter because of its ability to efficiently step down from our 7.4 voltage input from the battery while supporting up to 3 amps of current with 85 to 95% efficiency. For the 3.3 volt line, we chose a low dropout regulator, which is ideal for lower power circuits like the microcontroller. This allowed us to create a simpler design with minimal noise, which is ideal for the glove's compact battery-powered setup. Here we have the core components of the mainboard schematics. At the top right, we have the CP2102 USB to UART bridge, which allows serial communication between the ESP32 and a computer for programming and debugging. The top left includes additional logic for UART signal routing and reset control. At the bottom left is the ESP32 Room 32D, acting as the central MCU for the glove. On the bottom, we have the battery monitoring system using the BQ27441 fuel gauge, which helps us track battery life and charge levels. Here we have additional peripherals that interface with the mainboard. At the top right is the schematic for the LSM6DS3TR-G accelerometer and gyroscope, connected via I2C for motion tracking. To its left, we have the switch button inputs used to reset or control system modes. At the upper right is the USB-A connector schematic, which allows for external power or data input. Finally, at the bottom, we have the SignFlex sensors, with each one routed through series resistors and connected to analog input pins for gesture detection. Here we are focusing on the pin headers used to distribute regulated voltage and ground connections across the main board and to other modules. These headers include access to 5-volt rail, the 3.3-volt rail, and the ground rail, and were carefully positioned to simplify wiring to external components like the daughter boards or glove-mounted sensors. This modular approach also made testing and troubleshooting much easier during prototyping. We used a 4-layer design for the main PCB to ensure a clean and reliable signal transmission for high-speed digital communication, as well as provide low resistance path for current, ensuring stable power delivery, and reduce the voltage drops and ground bounce that may occur in the board. This 4-layer design also allows the power planes to dissipate more heat, unlike the 2-layer design, which doesn't have dedicated heat dissipation layers. This also gave us more routing flexibility when establishing the connections throughout the board. On the left, we have the AMS 1117 3.3 volt low dropout regulator, which takes in 5 volts from the buck converter and steps it down to 3.3 volts to power low noise components like the ESP32 and the accelerometer. We included 22 microfarad capacitors on both input and output for stability and decoupling, along with a 2 kilo ohm resistor current limiting and an LED to visually indicate when the 3.3 volt rail is active. On the right, we have the LM25960 5-volt buck converter, which steps down the 7.4 volts input from the lithium-ion battery pack to a stable 5-volt output. This design includes standard filtering components like 470 microfarad and 330 microfarad capacitors, a 33 microhenry inductor, and a fast recovery diode for smoothing out switching noise. These components ensure high efficiency and clean power delivery to downstream devices like the low dropout regulator and other 5-volt peripherals. We designed these daughter boards to be connected externally with the usage of the male header pins in order to avoid the risk of possibly having to redo the main PCB in case one or both regulators were to overheat if they were to be soldered directly on the main PCB.
Now let's move on to the software. One of the key components of our project was using computer vision. We use AI-powered image processing to recognize ASL gestures in real time. The phone's camera captures the user's hand with the glove on. Then we use image processing to analyze the frame and then classify the sign. And here are the main features. We use the smartphone's camera for live image capture, which makes the system portable and efficient. The images are then pre-processed using OpenCV to clean up noise and improve gesture clarity. Finally, we use a machine learning model built in with TensorFlow Lite to classify the gestures. For our computer vision system, we choose to use an Android phone, specifically something like Motorola ThinkPhone instead of the Raspberry Pi 4. And the main reasons that we choose an Android phone is because it has a built-in high-resolution camera with autofocus, so we didn't need to set up an external camera. It's also fully portable and has a great battery life and doesn't require an extra component like a battery pack or screen. And from a software perspective, it supports the Android SDK, OpenCV, and Java, which made our development faster and smoother. In contrast, the Raspberry Pi 4 would have required extra setup, power source, and would made our project less practical for a wearable mobile solution like SignFlex. And in this slide, we will compare the two gesture recognition methods. OpenCV with TensorFlow Lite, which we choose, versus MediaPipe hands. We selected OpenCV and TensorFlow Lite because it gave us the flexibility to train our own custom model, specifically for ASL gesture recognition. Unlike MediaPipe, which uses pre-trained model. Another key factor was the glove compatibility. MediaPipe performs best with bare hands, but our model works well even when the user is wearing the glove, which is very essential for our SignFlex project. It's also lightweight for Android deployment, customizable for feature updates, and better suited for training and adapting model based on our specific glove and dataset. We also use two main wired communication protocols, UART and I2C. We choose UART because it's simple and reliable point-to-point communication. It used to handle BLE communication between the ESP32 and the Android app, and it only requires two wires, TX and RX, which helps keeps our wiring minimal. I2C was used for internal communication with our IMU and fuel gauge. This protocol also uses just two wires, SDA and SCL, but can also connect multiple peripherals, which was important for saving PCB space and simplifying connection. We didn't use SPI in our system because it requires more pins, introduces additional complexity, and provides the speeds that weren't necessary for our application. For our programming, the ESP32, we compared the Arduino IDE and Visual Studio Code, and we ultimately choose Arduino IDE. Arduino IDE stood out because it's simple, beginner-friendly, and it also has official support for the ESP32. It also comes in with the built-in libraries that we were able to use, like flex sensors and IMU, which really helped us to streamline our development process. On the other hand, Visual Studio Code, while is a powerful tool, it requires more initial setup for ESP32 development and manual library management. It's better suited for a large-scale professional software project. And this flow chart shows how our SignFlex system operates in real time by combining computer vision with sensor data. Starting on the left, the Android camera captures a live image of the hand with the glove on. Then the image is pre-processed. For example, it's converted to a grayscale and enhanced using edge detection techniques like candy filtering. Then we use our TensorFlow model that we trained to recognize the gesture from the image and then send out the prediction to the Android app. And at the same time, on the right side, the ESP32 collects the data from the flex sensors and the IMU and then includes both sensor, the accelerometer and the gyroscope. And then this data will be sent to the Android app using BLE. The Android app then combines both the vision and sensor data to display the final recognized gestures on the screen and providing a real-time feedback to the user. And in this slide, I will walk through the process we followed to train our ASR recognition model. So we start by collecting gesture images and using the glove that we built, we customized, and then we take each letter from the alphabet from A to Z and put each letter into a different separate folder. And then each image then labeled with its corresponding letter. These labeled images were used to train a convolutional neural network, CNN, which was specifically tailored for our glove's shape and sensor setup on the glove. After training, we validated the model accuracy and made improvement, such as fine-tuning and architecture and applying data augmentation and also enhancing our recognition on some difficult signs. Once we achieve the high accuracy, we convert our trained model to TensorFlow Lite model for lightweight deployment on our Android app. This process was repeated and refined until our model performed reliably well in real-time conditions. In this slide, I will show how our model performed during training and validation over 25 epochs. On the left graph, you can see the accuracy curves. There is two lines. The blue line represents the training accuracy, which is reached almost 99%, meaning our model learned the training dataset extremely well. On the other hand, the orange line shows the validation accuracy, which fluctuates around 92%. That tells us that our model is generalizing very well, which is also expected in real-world testing. On the right graph, we have the loss curves. The training loss steadily dropped, showing that our model was successfully optimized. The validation loss also decreased but stayed a little bit higher than the training loss, which is also a good sign that our model is not overfitting. Overall, the gap between the training and validation performance shows that our model is accurate enough to be reliable during the real-time deployment. And after we trained our ASR recognition model with high accuracy, nearly almost 99% on the training dataset, we deployed it onto the Android app to test it in real-world condition. And we used the SignFlex glove, as you can see in the picture, and we tested it with the letters A and B. And as shown in the pictures, the model predicted the corrected gesture consistently, with response times of 24 to 27 milliseconds and accuracy ranging between 90 to 95%. This also confirmed not only the durability of our model, but also it was able to generalize well and from the training deployment, making it practical for real-time ASR recognition using the phone and the glove. We also faced several key challenges while developing the computer vision system in SignFlex. And first, there was a lighting and background variability. The model struggled to detect gestures under poor lighting and cluttered backgrounds. But we solved this by retraining the model using images taken to uniform lighting and one plane backgrounds. Next, were dataset limitation. Our pre-trained model didn't work well with our gloves, and our initial dataset was imbalanced. So we manually collected over 9,000 gesture images and balanced our data for each letter, and then we used fine-tuned MobileNet v2. We also ran into overfitting during training, especially due to a small dataset and similar-looking signs. But to fix this, we also added dropout layers, we used aggressive data augmentation, and I increased our dataset to over 12,000 images that were collected manually. On the technical side, the default Java camera view caused frame lag and compatibility issues, especially with the newer Android phones. So we switched it to Camera X, which handled our image process very smoothly. And lastly, we had a green tint and flipped image issue due to conflicts between our TensorFlow Lite model and OpenCV image formats. We fixed it by correcting the image proxy to make BAP conversion and adjusting the color format for OpenCV.
Now we'll be talking about the mobile app. Our mobile app is the primary interface between the SignFlex glove and its users. It wirelessly retrieves recognized hand gestures and displays them on a smartphone screen. We emphasize a user-friendly and a visual, clear design to make communication simpler and more inclusive. Its main features are real-time gesture display, text-to-speech, and fusion data between computer vision and flex sensor recognition. This flowchart shows how the app moves from initial checks like device compatibility and Bluetooth setup to core functions like translating gestures. If something fails, like Bluetooth, it alerts the user who can retry or then exit. Ultimately, this process updates the screen when a user recognizes a gesture correctly. Where the flowchart offers a more broad overview, the activity diagram details every step of how various actors like the user, glove, or database interact. In this instance, our main actor is a user plus external elements such as the glove or the database that might open the app, connect to Bluetooth, start gesture recognition, or edit other things like their profile. Here we compare different development environments like Visual Studio Code, WebStorm, and Android Studio. After evaluating our needs, we decided on Android Studio for this project. It's the official IDE for Android, offering integrated debugging tools, an emulator, and a layout editor tailored for native Android development. Hence, Android Studio strikes the best balance of official support and built-in features for rapid debugging and performance analysis for our style of app. For our mobile app framework, we explored frameworks like React Native and Flutter, but ultimately chose native Android for deeper control and tighter integration with device compatibilities. Native development lets us tap into Android's API directly without a bridging layer, potentially boosting performance and reducing compatibility issues. Our team has experience in Java and Kotlin, and the direct access to hardware features suits the real-time data handling from our Glove's Bluetooth module. This table breaks down the ease of use, mobile integration, data usage, real-time compatibilities, and maintenance across 4 popular databases. We picked MongoDB for its flexible JSON documents and alignment with sensor data from the Glove. It's relatively quick to set up and handles large or evolving data well. In this slide, we're highlighting how different wireless standards, BLE, Classic Bluetooth, and MSC compare in terms of their frequency bands, operational range, data throughput, power draw, latency, and security. We centered our design around BLE because it consumes very low energy, which is essential for battery-powered devices like our Glove, and also offers minimal latency, typically in the 3.3 to 6 millisecond range, which is ideal for real-time ASL gesture updates. By contrast, Classic Bluetooth achieves higher data rates, and MSC's very short range were not suitable, hence we chose BLE. This is our mobile app front end. We have 4 screenshots displaying some of the features we have in our user interface of our app. When a user first downloads the app, it will take you to the first screenshot, which is the register page. And once a user registers and logs in, it will take you to the second screenshot, which is our home page of our app, showing you the different features and buttons we have on our app, such as scanning for a glove, camera ASL, the dual ASL, the sensor data, and going back to your profile, and you can change your account status there. Once you're connected to the ESP32, in our instance, our ASL glove, and once a correct letter is detected, it will show you all the accurate data that we made in our ESP32 code, and along with our accelerometer data, giving you a detected letter. In this instance, it's F. If you click the dual ASL button, it will take Antonius's computer vision app that he made, along with the flex sensor recognition that we made, and combining the two for more accurate data recognition. In this page, it will still detect each the computer vision and flex sensor letter detection individually, but will wait for a more accurate threshold and combine the data for a complete combined recognition.
And now we will talk about the prototype testing. The glove was tested over 10 trials per letter for 2 letters, A and B, using both the flex sensors and the computer vision system, totaling 20 trials overall. For each letter, the average response time and accuracy were recorded individually in each trial. These values were then averaged across all 2 letters to determine the overall performance of each system. After recording the average accuracy values for both the flex sensors and the computer vision system, the two were combined to calculate the overall system accuracy. The image shown illustrates how the system operated during test trials using the flex sensors. In this example, when the user correctly signs the letter A, as detected within the calibrated sensor range and threshold, the application confirms the gesture by announcing A through text-to-speech and highlighting the corresponding text in green to indicate successful recognition. The computer vision system recorded an average response time of 22.9 milliseconds for letter A and 22.7 milliseconds for letter B. In terms of accuracy, it achieved 91.8% for letter A and 97.6% for letter B, demonstrating strong and consistent performance across both gestures. This high accuracy is largely due to the consistency of the image recognition model, which was able to pick up on clear visual patterns in each hand gesture. Because the testing environment had steady lighting and a fixed camera angle, the input images were clean and predictable, making it easier for the model to perform well. The model was also trained on well-labeled gesture data, which helped it quickly learn what to look for. Compared to the flex sensors, the computer vision system wasn't as sensitive to small changes in hand positioning or movement, which gave it an edge in terms of overall reliability and accuracy. The flex sensor system recorded an average response time of 47.6 milliseconds for letter A and 39.4 milliseconds for letter B. In terms of accuracy, the system achieved 80% for letter A and 90% for letter B, with a slightly lower performance compared to the computer vision. By combining the accuracies of both the flex sensors and the computer vision system, we achieved a combined accuracy of approximately 90%, successfully meeting our project's target requirement. In terms of response time, the flex sensors averaged 43.5 milliseconds, while the computer vision system averages 22.8 milliseconds. Both values are well below our response time requirement of 200 milliseconds, demonstrating that the system is not only accurate, but also fast enough for real-time performance. We did face some challenges with this project. The slightly lower accuracy that was found on the flex sensors compared to the computer vision system is largely due to the flex sensor's high sensitivity and tendency to drift over time. During testing, we observed that the raw ADC values from the sensors would gradually shift with continued use, requiring us to frequently adjust the threshold values in the code for each letter. This inconsistency made it challenging to maintain stable performance across multiple sessions. These findings emphasize the value of integrating computer vision with the flex sensors, as it helps compensate in situations where the flex sensors alone may struggle to correctly interpret certain hand signs, especially when the user performs them correctly, but the system fails to recognize them. We also had to replace our main power source, which was originally designed to be a power bank, but it was replaced with the lithium-ion batteries to ensure compatibility with the onboard fuel gauge system BQ27441, which could only support single-cell batteries. Another problem we had was that the original placement of the main PCB was meant to be on the user's arm, but since the accelerometer couldn't be on a separate board from the main PCB, we had to relocate it to the user's forearm, which we were able to by using a stretch mesh foam pouch, which was able to hold the main PCB securely on the user's forearm and properly use the accelerometer. Another issue we had is that the fuel gauge system was incorrectly designed due to incorrect net labeling and routing placement. But this was able to be solved by manually rewiring the traces on the PCB for proper orientation.
Some of those challenges we faced in developing the mobile application on the technical side was ensuring the reliability between the BLE link between the ESP32 glove and our Android app. We also had to optimize the responsiveness of our sign recognition feature, both for the flex sensor base and our visual based inputs, so users would experience minimal delay. In terms of integration, synchronizing data from the glove's flex sensors and camera-based gestures introduced timing and threshold challenges, while alongside displaying the battery monitor. Now we'll turn to administrative aspects of our project. We spent a total of about $360.44 on this project. This covers the core hardware such as the MCUs, flex sensors, along with the batteries and miscellaneous wiring and shipping for testing supplies. Breaking it down, the hardware sits around 24.4%, batteries at 28%, electrical components at 39%, and miscellaneous items at 8.5%. This is our work distribution. On the electrical side, Esteban and Madison handled the PCB design, battery monitoring, and integrating sensors like flex strips and IMU into the glove. For the computer engineering, Antonius developed the computer vision recognition and the embedded firmware for the ESP32, while I led the mobile app incorporating the BLE data and any computer vision features. Our timeline throughout this progress shows as this: over weeks 1 through 3, we would type loose ends on our PCB design and gathering necessary parts for more in-depth glove testing. From weeks 4 to 6, we will conduct our critical design review, testing and assembling our PCB and integrating it with the mobile app for real-time data. By weeks 6 to 9, our focus shift to refining the gesture recognition model, boosting accuracy on letters A to Z while debugging the app with real users. In weeks 10 to 12, we will finalize our main prototype in that time for the senior design demo. And weeks 13 to 15 will be our final presentation and project submission. In summary, our SignFlex offers an innovative, inclusive way to reduce communication barriers for deaf or hard of hearing individuals by tapping into modern sensor and mobile technologies. We made strides in merging hardware sensor integration with a straightforward mobile interface. In our final semester, we'll hone sensor accuracy, strain BLE collections, and ensure the database syncs seamlessly. We anticipate that SignFlex will become a solid framework for even more accessible communication solutions. Thank you for joining us in our SignFlex project.